This is the problem on the homework that was labeled bonus. I was not able to put the picture up here, but you remember the picture from the homework, or actually this was the, not homework, but the assignment from Friday that you may have done as homework. There was a kid on a slide, slid down the slide, went flying off and landed in a pool of water. And the question was, how far did they fly through the air? What's their lateral distance? That is their horizontal distance, their range. Well, this one, like so many of these others, it's a conservation of energy problem. Let me read the problem to you. If the height h of the water slide is 3.2 meters, that's how tall the slide was, and the person's initial speed at point A, that's the top of the slide, is 3.4 meters per second, what is the horizontal distance the base of the slide from the base of the slide to the splashdown point? Well, I've done this a little differently. I've written it all on the screen first, so let me just kind of walk you through it. This is the mechanical energy at the top. Let's do this. A moment. That should be a little easier for you to read. The mechanical energy at the top is going to be the potential energy plus the kinetic energy. And oftentimes at the top of whatever we're doing, there's no velocity, there's no kinetic energy because of that. This one, there is some kinetic energy. So we have mass times 10 meters per second squared times the height, 3.2. That's the height of the slide. Remember I told you in class that we can just take the relative change in potential energy. You don't have to figure out the total potential to the ground and then subtract at the bottom of the slide the total potential to the ground. You can, it all comes out the same way, but mass times acceleration due to gravity times the height of the slide plus 1/2 mass times the speed at the top, 3.4 meters per second squared. That's at the top. At the bottom it looks, well, that part looks identical. Mechanical energy is potential plus kinetic, but here we have the second half, this unknown mass, the problem did not tell us what the mass was, times 10 meters per second squared times 0 meters. We have said that we're going to act like potential energy is 0 at the bottom of the slide. So this whole term is going to go to 0 plus 1/2 mass times velocity squared. This is what we don't, there's two things we don't know right now. We don't know the mass of the kid, and we don't know the velocity of the kid at the bottom of the slide. But since there's no friction, I can set mechanical energy at the top to mechanical energy at the bottom. So just so you follow, this is this, and then this part, potential plus kinetic at the bottom, is potential plus kinetic at the bottom. The reason I wanted to do that is because we don't know the mass, but I highlighted here in yellow that the mass appears in all four of these terms. So I just divide each term by mass on both sides of the equation, and it goes away. So it doesn't matter that I didn't know mass. Actually, it turns out in this particular case, mass has nothing to do with it. I can kind of indicate that another way. Back when we were doing kinematics, we never even had mass enter into the thing. We didn't talk about mass until we got to Newton's laws, so mass has nothing to do with this problem. So I cancel them all out, and that leaves me this. Potential energy at the top, or it's not potential energy, but it's the leftover terms from potential energy. 10 times 3.2. Kinetic, the leftover part of kinetic energy, 1/2 3.4 squared. At the bottom, 10 meters per second squared, that's acceleration due to gravity. And it is 0 meters up in the air. So this term is going to go to 0 plus 1/2 the velocity at the bottom squared. So you can work out all of this, and all you don't know is velocity at the bottom. So I didn't bother doing that on the screen for you, but oops, sorry about that. Let's get that back in the shot here. But the velocity works out to 10.16. The kid launches from the slide, traveling perfectly horizontally because of the way the slide's drawn and built. So now it's in the air. We need to do some kinematics on it. What do we know? Vertically, the kid, when it's in the air, is going to fall 1.5 meters. That was from the picture. We initially didn't know time. We knew here. We knew that vertically it started at 0 meters per second, and that acceleration was 10 meters per second squared. We don't care what the velocity is, the vertical velocity when the child hits the ground. So from that, we use violet. I didn't bother writing violet down, but doing that gives us 0.55 seconds as the time that the kid's in the air. Well, this term that we just found a moment ago is the velocity that they launched at, horizontal velocity they launched at. I knew that, and I knew acceleration, horizontal acceleration is 0. So that means, now that I know the time, I again don't care about velocity later, and I would use violet again. And when I plug that in, I get that the kid traveled 5.6 meters. And that's all there is to that one. It was a conservation of energy problem followed by a kinematics problem. That's all there is.